Hello everyone and welcome back to an L582 modeling and control of electric machines and drives. Last time we started talking about the equivalent circuit modeling of a three-phase induction motor. As we see that we are talking about a three-phase machine that's balanced to three-phase machines. That means we're talking about a machine that have three-phase winding in the stator and three-phase winding and the rotor, and they're all balanced, means the winding are identical, have the same number of turns and separated by 120 degrees and have the same wiring dimensions. And fifth form, balanced three-phase voltage supply. So to model it, you just need to model one phase of them and you can know everything from this phase because they are just balanced, yeah. And we said just the theory of operation of the induction machine depends on that the electric current in the rotor comes by induction from the stator. So you push electric current to the stator and this creates magnetic fields, and the magnetic field is time varying with respect to the rotor, so the rotor has an induced voltage, and because we are short-circuiting the rotor winding, a current will move in those winding creating its own magnetic field, and the interaction between the magnetic field of the stator, which is the main magnetic field, and the magnetic field of the rotor, which is induced magnetic field, this interaction creates torque and the rotor starts rotating. That's pretty much like a transformer but with a moving secondary winding. So you can deal with an induction machine that looks like a transformer, whereas the primary winding is the stator and the secondary winding is the rotor. But as you know, now this secondary winding can rotate, yeah. So that was the equivalent circuit we just had for our induction motor. Again, it's a per phase equivalent circuit, so this represents just one phase. So starting from left hand side, here the power comes in, so that is your stator representation. Here is the R1 and JX1 and the impedance of the stator, resistance, and the leakage reactance. And this is the shunt element, which represented the core. It has a resistance part which represents the core losses. So for you to know, whenever you want to model any kind of a power loss in the equivalent circuit, it's represented by resistance. Okay, so R1 represented the power loss in the stator winding, which we call it the copper losses, and RC represented the core losses, which the losses in the core happened by the magnetic field, which causes two parts, eddy current and hysteresis. Go back to this lecture when we just talked about it in much detail before in synchronous machines. And now you have an ideal transformer now representing that you have a magnetic field crossing from the stator to the rotor and crossing power with it, converting power to the rotor side. So this is your rotor side going here, so you have a resistance and a leakage reactance again in the rotor. Okay, like we started driving last time, is the induced voltage in the rotor circuit totally depends on the slip. The slip is basically the difference between the actual mechanical speed of the rotor and the synchronous speed of the machine divided by the synchronous speed. So that means you have to have a difference between the mechanical speed of the rotation of the rotor and the synchronous speed, which is the speed of the magnetic field. Okay, otherwise there will not be any change in the magnetic field seen by the rotor winding, and that means no induced voltage or current or magnetic field in the rotor, and now you're blowing up all the theory of the machine. Okay, so the induced voltage is totally dependent on the slip, like you've seen here. So the actual one is the multiplication of the slip by the induced voltage at zero speed. So you have some induced voltage at zero speed because you have a relative speed. Now it's zero speed while the magnetic field rotates at the synchronous speed, so it is big, but with the increase in the mechanical speed, this relative speed starts going down and down, and this reduces the induced voltage down and down. So we just thought that the induced voltage in the rotor like this code is just the slip multiplied by the induced voltage at zero speed, and the same thing as the reactance of the rotor winding, because you know the reactance is just dependent on the frequency 2 pi fl. So it's also depending on the speed because the frequency of the rotor actually depends on the slip. Frequency of the rotor circuit equals the slip times the frequency in the stator circuit. Okay, guys? And this lends us about this derivation to this equivalent circuit last time. Okay, by just having or dividing everything here by the slip So it lined it out just by E rotor 0, which is the zero speed, and this is GXR0 and R rotor over S, yeah? And we said we don't like this transformer in between them. We want it to be a traditional electric circuit so we can deal with. So we just referred all the quantities from the rotor side to the stator side. And now we line it out with this simple electric circuit that we can solve and predict everything in our hand. Okay, guys? I'm not revising stuff, I'm just refreshing your memory what just we had already had in our mind since last time. Okay, guys? So the idea is we just line it out with an equivalent circuit looks like that. So here's again the equivalent circuit, or let me remind you that is per phase equivalent circuit of three-phase induction motors. Okay, and we started talking about it last time, so that's continued. Okay, so that is the thing we have just lined it out. Here the stator R1 and JX1, and here the shunt elements of the core RC and JXM, and that is V1, which is the voltage applied to the stator winding per phase. And here's the rotor representation. This guy is JX2 and this is R2 over S. Okay, I don't need to remind you that JX2 and R2 are referred values from the rotor side to the stator side, but most of the time we'll be just dealing with them and forget about this referring unless it is just stated out. Okay, so that is your guy. Here is I1, which is the stator current, and here is I2, which is the rotor current, and that is V1, which is the voltage applied to the stator. Okay, guys? Obviously, you can call this current IC and this current IM. Yeah? But I want to further represent this as much as looking as a transformer equivalent circuit. So I'm going to take this R2 over the slip and play a little bit with this. Okay? How this playing out to be? It is just like this. I say that R2 over S mathematically equals to R2 plus R2 multiplied by 1 minus S over S. You can drive this easily. Okay? The mathematical wise. So I'm going to take out this R2 over S from the equivalent circuit and just separate it on those two parts, R2 and R2, 1 S minus S. Okay? That is R1, JX1, and here are the shunt elements, RC, JXM, and here the rotor side, JX2, and R2, and here is R2 multiplied by 1 minus S over S. Okay? I did nothing here, it's just dividing this. Why? Because right now you will have here the internal impedance of the rotor, R2 plus JX2, like this, R1 plus JX1 in the stator. And this guy, we are gonna call it, it will just look like the same like the load in the equivalent circuit of a transformer. If you look back to the equivalent circuit of a transformer in your previous courses, it will just look exactly like this circuit, except that at the place of this resistance, you will have the load attached to the secondary of a transformer. We'll do the same here. So this looks like the load on a transformer, but it's dependent here. We call this dynamic load. Why? Because it depends on the slip. Okay? And you know this, so the slip equals ns minus nm over ns. Okay? So what's happening is, with the load changes, the mechanical load on your shaft or the motor changes, this changes the speed. Like we said, if the load goes up, the speed goes down. And changing the speed changes the slip S, okay? And changing the slip, changing this quantity, RT multiplied, R2 multiplied by 1 minus S over S, okay? So this term, that's why we call it the dynamic load, because that is the representation of the mechanical load in the equivalent circuit. Okay, so that's why we can represent any change in the mechanical load in our equivalent circuit, because that is an electric equivalent circuit, guys, and the load on an induction motor or any kind of a motor is a mechanical load. So how can you actually model the change in a load inside this electric circuit? By this term, R21 minus S over S. So the change in the load, it changes the speed, and the change in the speed, it changes the slip, and the change in the slip changes this term, R21 minus S over S. Okay, guys? So you can use any of those two circuits, that's fine. They are just pretty much equivalent, okay? We just separated R2 over S to be R2 plus R21 minus S over S, just for more, trying to be just more and more like the transformer equivalent circuit. Okay, guys? So, like we are just saying here, now I'm gonna jump out to have some quantification of all of these stuff. So from you can see here, we'll start now how the power just playing around this, like we just said at any kind of other machines before. So after having the equivalent circuits, we will start talking about the power flow diagram. Okay, and I'm gonna start by the motor mode. Actually, again, we are more concerned about the motor mode in this machine, but we will talk a little bit about the other modes of operation, also generator mode and stuff. But now I'm starting by the motor mode because that's the more important, guys. Okay, so I'm gonna start the power flow like we said all the time. So the input here, the power input, is actually electrical power input because that's a motor. Okay, and this is going to the stator. The power is coming from the supply going to your stator, okay? And you start losing. But I'm gonna just try to have you on time with me and just place you here the equivalent circuit, just because it is so much good representative for all those losses, okay? So here's our equivalent circuit, R1, JX1, and those are the shunt elements are RC, JXM, representation of the core, okay, and here is the rotor, JX2, R2, and here is the dynamic load, R21 minus S over S, okay? You know, this side here is the stator side, and this side here is the rotor side, and this guy is the core, RC plus JXM, okay? So back to the power flow. So the input power comes from here. So this input power is the power going here, P input to the stator, okay? And we start losing. Like we said, all the resistances in the equivalent circuit represent power loss. That's how things goes, guys. So R1 is the first power loss you will encounter just entering this equivalent circuit. The power goes to the stator winding and you start losing some power as copper losses on this winding. Whatever current move in a winding, you have losses because this winding has a resistance. We call this P copper 1, okay? And I'm gonna call this, or just that is the copper losses and stator winding, okay? Because those winding has resistance to the current passing through them, so you will have some power losses just trying to overcome this resistance. And this happens to be a thermal effect, heat up in this winding, okay? And the rest of the power just goes on furthermore inside here. And you encounter here RC, which is the core losses. So you start losing power again in the core. So that is P core, okay? Like we said before, that is the core losses, okay, caused by change in magnetic field. Like we said before, in the synchronous machine, it has two parts, which is the eddy current and hysteresis parts, okay? and both of them depends on the frequency. The eddy current depends on the frequency squared, while the hysteresis depends on the frequency. Okay, but both of them just needs a change in the magnetic field, and because we're talking about an AC machine here, so the magnetic field keeps changing all the time, so you have these core losses here. Okay, but those are the lumped core losses in the stator and rotor together. So the core losses here are just the core losses, the whole core, which is the stator core and the rotor core together lumped. Okay, and like we said before, the core losses is just, we know it by experimental work, and most of the time it's coming from empirical formulas, so it's just something we can play around with. Okay, and actually we can calculate it here, and we know how to calculate it a little bit. Okay, so this guy here, the core losses here. So yeah, and after this we just go here to the rotor side. Okay, now we're accessing the rotor side. Okay guys, so that means we are crossing, now we're the stator. The rest of the power here, we call it the air gap power, because that is basically the power going from the stator crossing the air gap towards the rotor. Air gap power. Okay, so the rest of the power now crossing the air gap from stator going to the rotor, so that's we call it the air gap power. Okay, and now you're entering the rotor, so again you're going inside here and you just meeting R2, which is the resistance of the rotor winding, and you start losing power again in the rotor winding. That is the copper losses 2. Okay, this is your copper losses in rotor winding. Again, the current moving in the rotor winding encounters resistance from its winding, and that's where you lose some of your power to overcome this resistance. Okay, and the rest of the power is now going towards this, our load. That is a representation of the load, and that is why we call this the converted power. Okay, P converted. Actually, we can call it P converted, or we can call it P developed, or we can call it P mechanical. They are all the same thing. Okay, that is the actual power converted to, or the converted power inside the machine. That's the power that's converted from electrical to be mechanical to go into the load. So this is the power going to the load. No, don't forget, we're now losing another power before we go, which is the rotational losses. Okay, so again we can call this mechanical losses, P mechanical losses, or we can call it PFW, which is P friction on windage. So they're all the same thing. And that's the rotational losses, is just like we said before, this is the friction and windage losses. The losses because you had friction with the mechanical parts on the machine, basically the bearing that holds the shaft while it's rotating, and windage, which is the friction with the air. Okay, so like you're seeing, it does not have any representation in the electric equivalent circuit here. You don't have a resistance here that represents the rotational losses. Why? Because we're considering it as a constant loss. So it does not have anything to do with change in the electric and the load and all that stuff. Okay, I'll be talking about this in a bit, but here's we losing the rotational losses, and that does not appear here on the equivalent circuit. And the rest of the power, the output power, that is a power that's going actually to the load. Okay, that is a mechanical power, and you can call it P output or call it P shaft. They are all the same, because that's the power going to the shaft of the machine transferred to the load. Okay guys, so that is your power flow in the motor mode, like you're seeing here. Like we all the time saying, all those guys going down here is the power you're losing all the way, so the summation of them give you the power loss. Okay guys, okay. And like we said, here is your stator side here, and here is your rotor side here, and this is the core. Okay, So the power is just going in this side here, that is going to the rotor. We call this the air gap power. That is the power that's crossing the stator going to the rotor, and that's why we call it the air gap power. Okay guys, that is the power we're talking about here. Good. So let me give you a couple of hints here, okay guys? So the core losses, P core, actually equals P core in the stator plus P core in the rotor, okay? We're just lumping them together, okay? And doesn't this a little bit not very accurate? They should be separated. Each core loss is just going to its way. It's not that much, okay? Because actually, again, P core, most of the time we just happen to have it in the field from laboratory tests or from lambda equations, and from equations coming from labs and from experience most of the time, and even from calculations using the equivalent circuit here, okay? So it's not that bad to just clump them together, the core losses in the stator and the core losses in the rotor. Let me remind you of something. The core losses is really as having two parts, the eddy current losses and the hysteresis losses. Yes, eddy current losses is just related to the frequency square, and this guy related to the frequency, so both of them really relates to the frequency, okay? And I hope you remember this, the frequency of the rotor circuits equal the slip times the stator circuit, okay? And in steady state, okay, where the motor reached its steady state speed and it's now just in a stable state working around, the slip, guys, is a very small value. That's for you to know. So the mechanical speed, which we said before, is just less than the synchronous speed. Yeah, it's less than it, but by a small amount. So yeah, you don't have very big difference between the synchronous speed and the mechanical speed, so that is by small amount, okay? And that means when you're calculating the slip, which is ns minus nm over ns, this numerator, which is ns minus nm, is very small, okay? Because like we said, nm is very close to ns, so this difference is very small. When you just divide it by the synchronous speed, which is basically large, you'll find this s is very small number. You'll find in 0.05, 0.04, something like that. It's not a big number, okay? So if you look at this again, this slip value is very small. That means the frequency of the rotor actually is very small in the steady state, and the steady state is actually where we are looking at most of the time, because that is the state where our motor working most of the time. We're not all the time concerned about the transient periods, but you're looking most of the time at the steady state period, okay? So at steady state period, the frequency and the stator is high, which is mostly the 60 hertz coming from the grid, while the frequency of the rotor circuit is very small, because that will be the 60 hertz multiplied by the slip, and the slip is a very, very small. So the frequency in the rotor will be 3 hertz, 4 hertz, 5 hertz, something like that, okay? And that's why actually the core losses in the rotor will be much, much, much smaller than the core losses in the stator, because like we said, it depends on the frequency, yeah? So because like that, the frequency in the rotor is much less than the frequency in the stator, and that means the core losses in the rotor is much, much less than the core losses in the stator, okay? So we just assumed to add the rotational loss, the core losses, sorry, in the rotor to the stator, and just lump them together in P core. We will not be making something that is not accurate, okay? It will be a very, very minor difference if you try to just separate them and just let the core losses of the stator to be at the stator side and the core losses in the rotor to be at the rotor side. We're trying to just simplify calculations to be reasonably accurate, okay guys? That is the first thing for you to understand. The second thing here are the rotational losses. Rotational losses, like we said, or mechanical losses, depends on the speed, okay? So with the change in the speed, actually if the speed goes up, rotational losses should go up, but actually we neglect this. So rotational losses, yeah, it depends on the speed, and the speed actually depends on the load, okay? And the speed, yeah, depends on load, okay? But actually the change in P rotational with the change in speed here is very small, okay, as actually change and speed with load is very small here, okay. So like we said, yeah, the change in the load changes the mechanical speed and m, okay, but it does not change it in by very big numbers. Actually, the change will not be that high, okay. That's how the things work on motors, or specifically in induction motors. You'll not find very big change in speed, okay. So yeah, the change in the load changes the speed a little bit, and the change in speed should change the rotational losses a little bit, but this change is very small, so actually we can just neglect it and assume P rotational does not change by change in load, okay. And that is why we do not, or just we are not representing it by a resistance here in the equivalent circuit. We just assume that's constant and take it out of the calculations, okay. We just calculate it like this. After we calculating the P converted here, okay, we just subtract the rotational losses from it as a losses to get out the mechanical output power and the shaft power, okay. That's how we are saying here, okay guys. So we're assuming that the rotational losses are just constant, okay. And by the way, sometimes we also assume the P core also does not change with load change. Sometimes also, yeah, P core, we just find out that the core losses actually does not also change much with the change in the load, and that's why it's just accurate enough to consider P core constant and make it lumped with the rotational losses, okay. And we call them the P core plus P rotational, we call them the constant losses, okay. So yeah, in some machines we just find out that even the core losses does not change that much when they change in the load, so we just don't bother with it and just assume that's constant. And in this case, you just find the equivalent circuit to be like that. That is R1, JX1, and that is the core representation, just JXM. And you don't bother about RC anymore because you're just assuming that is constant, and just you take it out of the equivalent circuit and lumped, make it, yeah, lumped with the rotational losses like says, and that is R2 over S, or you can just make this R2 plus R2 1 minus S over S. It's up to you. So that's the equivalent circuit you can use if the core losses is assumed constant, okay guys. You just don't have RC to just bother with, yeah. So use this equivalent circuit if P core is considered constant, okay. If you don't consider constant, now you use this equivalent circuit and just have RC in its place and just deal with this, okay guys. Sounds good. And speaking of that, we can now try to quantify those power and power losses. So if you want to calculate the input power, which is basically the electric power going to the machine, so it's an electric power to calculate. It's that easy. Square root of 3 V line to line I line cosine theta, just like any constant before. Or it is 3 V phase 1, we call it V1 I1 cosine theta. Okay, and that is the thing we use most of the time because we're using the equivalent circuit. So everything is a phase values. Okay, so V1 and I1 is phase quantities. Okay, so V1 is the voltage applied to the stator, so all the time we're calling 1 as the stator values and 2 as the rotor values. Okay, so V1 is the stator per phase voltage. I1 is the stator phase or per phase current. That's in amperes and that's in volts. And the theta is like, is the angle between V1 and I1. Okay? So if you want to calculate it in phase, multiply it by 3 because they're 3 phase quantities. If you want to calculate it in line to line, use multiplication by square root of 3. Yeah, don't get confused. After this, the copper losses in the stator, P copper 1, is basically 3 I1 as a magnitude square multiplied by R1. And please do not calculate this using the magnitude and angle of I1 because, that will not be good. It's a power, so it does not have angles. So all the time we're using here the magnitudes of the currents and voltages. Yeah. Good. That is the P copper 1. After that, the P core. So the P core is the same thing, 3IC square, also as a magnitude, times RC. Okay. This, if you were using the very starting equivalent circuit here, by the time, or just by the way here, this equivalent circuit, we call it the exact equivalent circuit. Okay, it's as exact as possible. Sometimes we call this equivalent circuit the approximate equivalent circuit. Okay, it's just a thing, because here we're just approximating that the core losses is constant and we get rid of the RC. Okay, that's an approximation, that's why we call it an approximate equivalent circuit. So this P core, if you doing or using the exact equivalent circuit, yeah, if you're using the approximate, that means you don't have RC at all. So yeah, the core losses is just a constant loss you have, or it's given to you in the problem, or you just estimate it in the lab, so you don't need to calculate it at all. Okay, after this, here the P copper and the rotor, P copper 2 is 3I2 as a magnitude square times R2. The converted power, or the developed power, or the mechanical power, they're all the same thing, is actually the power that's going to the dynamic load here. Like we said, it is the power that is converted into mechanical power. So that is the power that is going to this guy, to the mechanical load. Sorry, to the dynamic load. So it is 3I2 as a magnitude again squared, R2 1 minus S over S. So R2 1 minus S over S is your dynamic load. So the power in this dynamic load, 3I2 squared multiplied by this resistance, 1 minus S over S, is the power that is converted from electrical to mechanical source. Okay, guys? And the air gap power, which is the total power going to the rotor, is 3I2 as a magnitude square R2 over S. Okay? Because like we just said, this guy equals the converted power plus P copper losses in the rotor. That is the total power here, back here to this guy. So that is P air gap, like we've seen it here. It is the total power going to the rotor, so it is the summation of P copper 2 and P converted. Okay, guys? So it can be calculated from this equation, 3I2 square R2 over S, or by addition of P converted or P copper losses in the rotor. It's your way. Okay? Okay. So yeah, having this, by the way, that's something to consider. So if you go back to the equivalent circuit, sorry, the power flow, you see that the air gap power, and you're losing some of it as copper losses in the rotor, and the rest of your converted power or developed power, like this. Okay. From this equation, you can find that is very interesting relationship to find. That is the air gap power to P copper losses in the rotor to the converted power is 1 to S to 1 minus S. Keep that in mind. That's very useful in your calculations and or your problems. It will save you a lot of time. What I mean by this is just if you know any one of those powers, those three powers, air gap power, copper losses in the rotor, P copper 2 or P converted, and you know the slip, you can just find all the others without detailed calculations. Okay? How? From this here, you can say that the B copper losses in the rotor P copper 2 equals S times air gap power. And the converted power equals 1 minus S times the air gap power. Yeah? And the P copper 2 will equal S over 1 minus S times the converted power. And keep doing that, okay? It's just fraction relationship. Okay, guys? Okay. So yeah, you just need to calculate just one of them using the current. So calculate air gap power, maybe a 3I2 square R2 address, and you don't need to calculate the other two using the currents and all that stuff. It's just that easy using this ratio relationship. You can use it directly. Okay, guys? That sounds good. And after this, you can find the output power, or call it the shaft power, whatever you want to call it. Okay. So this will equal the converted power or the developed power minus the P rotational losses or the friction windage losses or whatever you want. So that all the time is a constant value. It's given in the problems or estimated in the lab. So that is something we cannot calculate actually. Okay, so you can just do it like that. Okay, and before we go, it is just as I remember, if RC is neglected, if you don't have RC and using the approximate equivalent circuit, that means the core losses is assumed constant, okay, and lumped with the rotational losses, okay. And this thing, if you want to calculate the P output, it will be P converted minus the constant, we call it P constant, which is the P core and P rotational added together. Okay, guys? Okay. And as usual, all the time you'll need to calculate the percentage efficiency, which is the P output over P input multiplied by 100. Okay, guys? So, it's how to actually mathematically quantify all the powers and the power losses inside this machine and to understand what's happening inside this. It's very, very important to deal with, so keep that in mind. Okay, guys? Okay. Yeah. And yeah. Speaking of powers, we can also find out the torques. Okay. And just like we did before, the torque of the machine, we call it torque motor. Sometimes we call it the torque developed. So it is the developed torque or the motor torque. Okay. Or yeah, it's all the same thing. Is basically the converted power or the developed power, they are the same thing, divided by omega m, like any other machine actually. Okay guys? But because we know this, I'll just give you this hint here. Okay? Remember when I said here that is the converted power is 1 minus S times P air gap? The converted power equals 1 minus S times the air gap power, yeah? And we just know this Nm, or let me have it like the slip equals Ns minus Nm over Ns. By the way, you can find it from the omegas. It's omega S minus omega m over omega s. You know the difference between N and omega, yeah? The omega is the speed in radian per second, we call it the angular speed, and N is the RPM speed, the speed in revolution per minute. And you can just convert them easily. Omega equals 2 pi over 60 times N, yes? And from this, you can just find this Nm will equal 1 minus S times Ns. It's just the same law. It's mathematical tricks. And that will give you omega m equals 1 minus S times omega s. Yeah? They're all just math. So have this in mind. Omega s equals 1 minus S omega s. And the converted power is 1 minus S times P air gap. Okay? So I can just substitute in here. Take out the converted power from the law of the torque to be 1 minus S times P air gap, and omega m to be 1 minus S times omega s. Now you can take 1 minus S out, and this will give you P air gap over omega s. Okay? So, if you want to calculate the motor torque or the converted torque or the developed torque, you can calculate it from P converted over omega m, or from air gap power over omega s. Omega m is the mechanical power of the rotor, omega s is the synchronous speed. Keep that in mind. Omega m is the mechanical speed, the actual speed of the rotor, and omega s is the synchronous speed, which is the speed of the magnetic field. So, yeah, from here you can calculate your torque. Okay? By the way, this guy is the developed or converted torque, not the actual torque going out. Why? Because it depends on the converted power, the power that's inside the machine before losing the rotational losses. And that's why if you want to calculate the output torque or the shaft torque, whatever you want to call it, so T output or call it T shaft, that will equal P output over omega m, not this guy. Okay guys? So yeah, this torque we call it the developed torque or the converted torque, or yeah, sometimes even we call it the mechanical torque. So you can find it from here. But if I want you to find me the shaft torque or the output torque, that is the actual torque going to the load, that will be PO over omega m. Yeah, and that can be called also T, yeah. Shaft or 2 mechanical, sorry. Yeah, okay. That is the torque that actually go into the load. You can calculate it here from P output, okay? And you know, P output will equal P converted minus P rotational, or P constant if you have the core losses lambda with it. Okay guys? Okay, that sounds good. So this is how actually to deal with all the power and power losses and all that stuff going on with this machines. Okay. Okay. So we know now we can, from all of this, is to estimate all the performance of the machine, find all its power and power losses and torques, and all the stuff here just known or using the equivalent circuit of the machine. whether it is the exact equivalent circuit this here or the approximate one, by just assuming RC is not there, okay? But if you can do this before doing anything, you have to find all these parameters: R1, X1, R2, X2, RC, XM. Okay, those parameters are unique for each machine, and you want to find them before you can just do anything. Okay, guys? Like we did before with the synchronous machine, we're gonna test this machine in the lab to find out those parameters. Okay, guys? So this takes you thus to find out, before doing anything else with this equivalent circuit, is how actually to find it. So it is the determination of equivalent circuit parameters. How to find this? Using lab testing. How to test this machine in the lab to find out its equivalent circuit parameters. Okay, guys? Like we just did before the the synchronous machine to find its equivalent circuit parameters, I'll go here again doing the same thing with a three-phase induction motor in a lab. Just like the synchronous machine, we have three tests, if you remember: the DC test, the no-load test, and the short circuit test. We'll be having three tests here in the induction machine. The DC test, also like the synchronous machine, and this we call it the no-load test, and the locked rotor test. Also three tests to find out. And I'm gonna start talking about the DC test. That is the first test. Okay? So how to do this? We'll play like this. Okay? Apply DC voltage to any two terminals of the stator and measure voltage and current. That's it. Why I'm saying two terminals? Because you do know that for the stator you have three-phase winding. So in the stator you will have the terminals of the winding coming out, yes? So that is the terminal box of the machine. And most of the time you will just have three terminals out. One for A, one for B, and one for C. Okay? So typically you will need 6 terminals because you have three winding, yeah? So three-phase winding. So each winding has 2 terminals. But most of the time you do not have access to all the 6 terminals because the stator winding will be internally connected as Y or delta, and you will have just the line terminals out. You will not have access to each phase individually. So that's why I'm saying do it like that. You will connect any of those 2 terminals, say A and B, to a DC source here, VDC. So the current going here will be IDC, and you just measure the voltage and current. I place voltmeter over here. Okay. Or let me say that the voltmeter actually going to the terminals. So that will be more accurate. That's the voltmeter going to the terminals. And place an ammeter in series here to give you the current, IDC. Okay. Why are we just placing just DC and all that stuff? If you remember, that's the same thing we did before the synchronous machine, okay? So the whole point is applying DC voltage will cancel out all the reactances, okay, because the frequency will equal 0, and you know all the reactances, all the x's equals 2 pi FL. So yeah, with the frequency equals 0, this x all the x's actually, which is 2 by FL. So by having a DC and this frequency goes to 0, so all the x's are 0. And you just don't have anything in this stator you are just applying the voltage to but the R1. Yeah, so we are applying DC voltage to the stator, guys. So yeah, this will be just having an access to the stator terminals, and you just don't have anything but this guy. Okay, that's why we're using DC, not AC. So now we have VDC and IDC just measured like this, and what's after this? So you find from those guys the measured R. So R measured equals VDC over IDC. Okay, and this R measured is the resistance of the stator winding, R1. Now let's play around with the connections here. We are connected those to the A and B terminals, so it depends on the internal connection of the stator winding, if it is delta connected or Y connected. Like we said, it's just they're connected internally. Okay, so if it is connected like Y connected, which is the most of the time the connection we'll be dealing with here, this guy will be just like this. You have three-phase winding, that is R1, and that is R1, and that is R1. Okay, and those are the terminals you have outside. This is A, that is B, and that is C. And you connected your stuff between those two guys, A and B. Yes, that is VDC and that is IDC. So if you divide VDC by IDC like in seen here, like this, you will be just having the total resistance seen between those two terminals, like you see in here. Yeah, like you see in here, the current will be moving in those two resistances, R1 and another R1, because this now is opened, C1. Okay, so from this, VDC over IDC, which is the R measured, is equaling to R1. So to find R1, which is the stator resistance, you just divide this measured resistance VDC over 1 DC over IDC, sorry, by 2. Okay, guys? So you don't just get VDC over IDC and just move away, because now it's not the actual resistance of the phase. Now it's the resistance of two phases added together, because that is Y connected. Okay? But what about if it is delta connected? So it will have the resistances like this. That is R1, and that is another R1, and that is the third R1. Again, though, the terminals you're having outside, that is A, that is B, and that is C. And you're connecting your source between A and B, so that is VDC, and the current going here is IDC. So like you've seen here, if we just divide VDC by IDC in this case, which is giving you the measured resistance, R measured, it is actually the resistance seen between those two terminals. And if you look at those, it will be the equivalent of those together as this. So you will have those as series connected, R1 and another R1, and the equivalent of those will be just in parallel with the third one here. It is basic circuits, guys. Okay, so this guy here will be 2R1, which is two of those in series, and that is in parallel with another R1. Yeah, and to find this, you know, two parallel resistance, so it is 2R1 multiplied by R1 over 2R1 added to R1. Is how to find the equivalent of two resistors, the equivalent of them together. So this will give you 2 over 3R1. That means if you want to find R1 in case of a delta connected, it will be equaling 3 over 2 times R measured, which is 3 over 2 VDC over IDC. That is R1 in case of delta connected. While, yeah, from here, R1 in case of Y connected, like we said, so R1 in case of Y connected will be just half of the VDC divided by IDC. Okay, guys? All of this because you don't have the terminals of an individual phase out like we had before with the synchronous machine. Here, we just most of the time having just the line terminals. That means the machine is internally connected like Y or delta, the stator I'm talking about. So, you don't have other options but to just apply the DC voltage between any two terminals and to find out yourself what you are measuring and what is this to be just translated internally. And that's like we've seen here. Okay, guys? So that's the first one. That's the DC test, and it is used to find R1. Okay? Okay. So yeah, that's it for today. And next time we'll be continuing talking about those tests. I'll be talking about the other two tests, the Lec22 test and the no-load test. Thanks so much, guys, for joining me today, and I'll be happy to be seeing you next time.